Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problem number 1 of the AP Calculus AB free response question for 2017. This problem focuses on table and amounts. If you want to gain access to a wide variety of prep resources for the AP exam, you can visit our website at mathgotserved.com under AP Calculus. All right, let's take a look at question number 1. It reads, a tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values for a of h are given in the table above. So we have the table here showing the selected values of a of h for a specified h value. Question 1a. Use a left Riemann sum with 3 sub-intervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measure. Alright, so let's start off by writing down the formula that's going to guide our problem solving process. So, formula is as follows. So if we want to find the volume given area and height, so remember the basic geometry formula, volume is area times height, area of the base times height. But what if you have a variable area of the base? Then you have to make use of calculus tools, okay? So the volume V is given by the integral from a to b of the area of the base with respect to time times the height dh. Okay, so this is the formula we're going to be using. Now, what if you want to estimate this integral using Riemann sum, so the left Riemann sum or the left rectangular approximation? So this problem we are to approximate this using left rectangular approximation or left Riemann sum with 3 sub-intervals. Okay, so let's go over the formula for that real quick. Whenever you're dealing with approximation of integrals in an AP exam, you're either going to use the left Riemann sum, the right Riemann sum, the midpoint sum, or the trapezoidal approximation. Okay, so here we have 4 input and output values, so let's place them here. So I'm going to just call them x and y for the case of simplicity. Okay, so x and y, these are the independent are on the top and the dependent variables are on the bottom. Alright, so we have 1, 2, 3, 4. So let's say we have x1, x2, x3, and x4, okay? And then y1, y2, y3, and y4. So if you want to estimate the integral using the left Riemann sum, LRAM, what you're going to do is you're going to take all the points to the left of the right endpoint. But before we do that, let's specify the base of our rectangles. So it's simply going to be x1 to x2, that's going to be the first width. And then from x2 to x3, that's going to be the second width. And then from x3 to x4, that will be your third width. Okay, so we're going to have 3 rectangles. So this is width 1, width 2, width 3. And length times width is basically the height of a rectangle, right? So we know that the area of a rectangle is length times width, right? So for left rectangular approximation, what we're going to do is we're going to cross out the right endpoint. So you cross this out and you use everything to the left of that. Alright, so if we do that, we're going to have, we're looking at y1 for LRAM, we're looking at y1, y2, y3, y4 is gone. Okay, so it's going to be y1 times w1 is the area of the first left rectangle, plus y2 times w2 is the area of the second one, plus y3 times w3 is the area of the third one. How about the right rectangular approximation? The problem doesn't ask for it, but let's just go over it anyway, because you need to know that. If you want to do the right Riemann sum, guess what? What you do for the right Riemann sum is you take all the points to the right of the left endpoint. In that case, you're going to cross out y1 and then you use y2, y3, y4. So let's write down what the formula is for the right Riemann sum. It's going to be, instead of y1, you're going to go y2 times w1. The widths basically stay the same. Y3 times w2 plus y4 times w3. That's the right Riemann sum. How about the midpoint rectangle approximation? For the midpoint, all you simply do is you average y1, y2, y2, y3, y3, y4. That will be your lengths, and then w1, w2, and w3 will be there. In most cases, when they ask you for midpoint, they normally have a situation where you have a value in the center of your widths. How about your trapezoidal approximation, your trap app? Trapezoidal approximation, you have 3 trapezoids, right? So you're going to compute 1/2 sum of parallel lines times height. So the parallel lines are y1 and y2, or the bases, and that's the height. So 1/2 y1 plus y2 multiplied by the first width plus 1/2 y2 and y3 is the next trapezoid, y2 plus y3 times w2. Let's move that to the left a little bit, times w2. And then your final trapezoid, 1/2 y3 plus y4 times w3. Now, if you look at these 3 approximations, you notice how we always use w1, w2, w3 over and over again. So whenever you're presented with a problem like this, you want to find those first, and then shift your attention to the output values. Alright? So you need to know all these 3 formulas cold in order to do well with your integral approximation using Riemann sums. Okay? Alright, so for this problem, we're going from 0 to 10. Let's take a look at the table here. This is going to be our starting point. This is going to be our A. And we're going all the way to B. Alright, so the volume for this scenario that we're dealing with is going to be, let's apply this formula to this situation. Okay, V is the integral from what to what? The integral from 0 to 10 of the area with respect to h times the h, and we're approximating this using the right Riemann sum with 3 rectangles. Okay, alright, so let's do it. LRAM with 3 rectangles means that we need to find the widths first. So this is going to be first width. 2 minus 0 is 2. The second width, 5 minus 2 is 3. And then the third width, 10 minus 5 is 5. So one caution, let's go over that real quick, has to do with widths of rectangles. Now, a lot of textbooks, when dealing with Riemann sums, always present scenarios where you have equal subintervals. But in the AP exam, it's rare to see subintervals that are equal. In this case, notice there are subintervals. We have widths that are 2, 3, and 5. They're all different. So they want to assume that if the first width is 2, everything else is going to be 2. That will be a bad mistake to make. So calculate the widths of each rectangle or trapezoid and then compute the areas individually to minimize the odds of making mistakes. Okay? Alright, so LRAM, we are doing the left rectangular approximation. What does that mean? We're going to take all the points to the left of the right endpoint. So we're going to cross 2.9 out of the picture. Okay? So for the rest, first rectangle, we're going to look at the length. 50.3 times the width, which is 2, plus the second rectangle, the length, 14.4 times the width, which is 3, plus the third rectangle, third and final, the length, which is 6.5, times the width, which is 5. Okay? So this is a calculator section, so we're going to use our calculators to compute this area, volume. Alright, I'm going to be making use of the TI-89 titanium calculator for this presentation. So let's do it. 50.3 times 2 plus 14.4 times 3 plus the last area, 6.5 times 5. Okay? And then press enter, and that's your approximation. Okay? So what does this tell us? The volume is approximately 176.3. Now, what is the unit? Remember, the problems asked you to indicate units of measure. Okay? So one big tip that you want to keep in mind, sometimes it's obvious to determine what the unit is. For instance, volume is easy to determine, but sometimes it might be unclear what the volume, what the unit of your final result is. So one tip that can really help you is, this tip is concerning units, is that the formulas the formula you use can help determine the units. Okay, so sometimes you ask yourself, what's the unit of this? So you just go to the formula and then plug in the units that you're given into the formula. You're good to go. So for instance, in this case, the formula for volume that we're looking at was the integral of A of h times dh. Okay, so here, what's the unit for area? Square feet, right? So it's feet square times dh is an infinitely small height. But so forget about the d, look at the h. What's the unit for height? Feet. So the integral of A of h times dh is basically a situation where you're multiplying an area, feet square, by a height, dh. What is feet square times feet or foot? Feet square times foot is feet cubed. So that is the unit here. Okay? In this particular problem, it's obvious that it's feet cubed, but sometimes when you're dealing with more sophisticated problems where it's not that clear, the setup of your formula can tell you exactly what the units are. Okay, now let's talk about the scoring guidelines for this particular problem. For this part, 1A, you earn 2 and a third points. Okay, we'll talk about the third points later. How to get the 2 points? First one has to do with the accurate setup of your Riemann sum. Okay, so you see this LRAM right here. If you set this up correctly, you earn 1 point. Okay, and then if you approximated, basically you plugged in this value into your calculator correctly and you had 176.3, you earn another point. Okay, and then if you specify the unit feet cubed, you earn a third of a point, but that is not guaranteed. This 1/3 of a point is contingent upon you specifying the units in all the parts of this problem that requires units. Okay, so let's say you earn a third of a point here by stating the unit, and in the other 3 parts you stated the unit correctly, then automatically you have 1 point thrown in into your final sum. Okay, so in this particular part, you have um, 2 points for this particular problem, and then plus 1/3 if you add the correct units to all the parts of this problem that requires for you to add units. Alright, now let's take a look at the B part. The B part states, does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Okay, so they're just trying to make sure that you have a visual understanding of what left rectangular approximation looks like, and that you're not just randomly following some formulas. Okay, so what you want to remember before we solve the problem, you want to recall the following. First of all, if if f of x is decreasing on an interval, okay, then the left Riemann sum, or the left rectangular approximation, guess what? If it's decreasing, the left rectangular approximation is an overestimate, okay? Is an overestimate. Okay? And on the flip side, if f of x is increasing on an interval, then the right Riemann sum, or right rectangular approximation, guess what it is an overestimation. Okay, is an overestimate. Alright, so additionally, so if f of x is decreasing on an interval, LRAM is an overestimation, and then guess what? RRAM is there. If a function is decreasing, LRAM is an overestimation, and RRAM is an underestimation. Okay? Now on the flip side, if the function is increasing, RRAM is an overestimation, and LRAM is what? LRAM is an underestimation. So LRAM is an underestimation. Okay, so just remember, decreasing LRAM is over, increasing RRAM is over, and then you can flip it from there. Let me give you a visual as to what I'm talking about here. So let's take a look at the increasing case first. So let's sketch the graph. A function that's decreasing. Now let's say you don't remember this formula. You don't have to remember this. If you're in doubt as to exactly what's going on, all you just have to do is draw the rectangles, draw a graph that follows a pattern, and put in the rectangles. Okay, so let's look at the decreasing scenario. So you have a function that's decreasing here. Decreasing. What does the LRAM look like? The left Riemann sums. So for the left Riemann sums, let's say we have just 3 rectangles. What you do is you trace all the points to the left of the right endpoints to the graph, and use those to create your rectangles. Okay, so for the LRAM, you ignore this, and then you take this point right here, this point right here, and this point. These are the points that define your rectangle. So let's draw it in. So bam, there goes your first rectangle. Draw it properly. So you have your first rectangle. This is not working. Have your first rectangle, and then, alright, I'm just going to use the ruler. So you have your first rectangle, your second rectangle, and your third rectangle. Now what do you notice here? You notice that the rectangles occupy an area that's bigger than the area of underneath the curve. Okay, so let's just make a remark right here. Let's say the area is the integral from a to b of the function. In this particular case, what's happening is that the left rectangular approximation, LRAM is what? LRAM is greater than the area, which is the integral from a to b of f of x dx. So since the area is greater, then it automatically tells you that LRAM is an overestimate. Okay? Now let's take a look at RRAM. Alright, so for RRAM, we're looking at all the points to the right of the left endpoint when we are creating our triangles. So let's go ahead and take a look at what RRAM looks like. So for RRAM, you're going to start from here, this point right here, and then you create your triangles. So we're looking at starting from here, this point, that point. Those 3 points define the right rectangular approximation. So let's go ahead and draw in the rectangles. So for RRAM, this would be your first one, first rectangle, and then this is your second rectangle right here. And this is your final rectangle right here. Now what do you notice about the area underneath the green rectangles? If you add up these 3 areas right here, let me highlight it for you. What do you notice happening? This area and this area and this area. It doesn't occupy all the area underneath the line, the function. Okay, you have spaces here. What does that mean? It means that the right rectangular approximation or right Riemann sum form an underestimation of the area. Okay, so this one is overestimate, and on the flip side, the right rectangular approximation is smaller than the exact area, integral from a to b of the function. So that implies that we have an underestimation. Okay, now let's take a look at the flip side. Let's examine a function that's increasing. Okay, so change the behavior here. We have a function that's increasing. Now, can you see why this second statement would be true? Increasing when right rectangular RRAM is going to be an overestimate, and if it's increasing, LRAM will be an underestimation. Let's start with RRAM first. So let's say we have 3 subintervals, 1, 2, 3, and you want to draw your right Riemann sum rectangles. You start from the right endpoint, trace to the graph, first point, second point, third point. Okay, you basically specifying the right vertex of the top of your rectangles. So let's draw in the rectangles there and see what happens. Okay, so you trace this up. Bam, it's already over. You see that? The RRAM is an overestimate if the function is increasing. Like that. And then this one like that. Bam, overestimate. Okay, so let's write down the remark real quick. Alright, so if we write down the remark here, in this situation that we have, the right rectangular approximation is greater than the exact area underneath the curve, which is integral from a to b of f of x dx. Okay, and what does this imply? This basically implies that we have an overestimation for the right rectangular approximation. Okay, and then let's look at the flip side. What happens for the left rectangular approximation when the triangle, if the function is increasing? So we start from the left endpoint. You have a point here, a point here, a point here. You notice the difference? When you're creating your LRAM triangles, you start from the left, trace it to the function. Okay, and then if you're doing your RRAM, you start from the right, trace it to the function, and you go from there. Alright, so let's draw in our rectangles, and you'll see why we have an underestimation for the left rectangular approximation. So this is your first rectangle right here. Bam. Underestimation because you have an area right here that's been left out. Next rectangle, further underestimation, area left out here. And then final one, Bam, you can clearly see we have an overestimation in all three cases. So what's the conclusion here? The conclusion here is that the left rectangular approximation is less than the uh, exact area, and that tells you that it's an underestimation. Okay, so this is just the reasoning that should guide your response. You don't have to do all this if you don't know, if you don't have to. Okay, so in this particular problem, the big question is this function increasing or decreasing? So you just take a look at the table and look at the behavior of a of h. 50.3, 14.4, 6.5, and 2.9. I think that's what that is. So we can clearly see that the function is decreasing. So since the function is decreasing, what's our conclusion? Well, since the function is decreasing, let's write that down. The LRAM is going to be an overestimate. Okay, so we have, this is the scenario that we're looking at for this particular problem, decreasing. LRAM is an overestimate. Okay, so we'll write down this solution. Let's see what the question is so that we can know how to phrase our answer. The approximation in part A. So you start with the question. The approximation in part A is what? Is an overestimate. So the question is this sufficient just to say, oh, it's an overestimation? The answer is no. You're asked to explain your reasoning. Okay, so to earn the full points for this problem, you want to state the answer and the reasons. So the approximation in A is an overestimate because this is your explanation, because the area A of h is the area A of h used in LRAM, the area A of h used in the left rectangular approximation, or used in the left Riemann sum, used in the left Riemann sum is doing what? Is decreasing. Okay, using left Riemann sum is decreasing. Alright, so this is the explanation as to why, or this is the reason as to why your answer was an overestimate. Okay, so for this particular problem, you will earn exactly 1 point. Alright, let's take a look at 1C. It reads, the area in square feet of the horizontal cross section at height h feet is modeled by the function f given by f of h equals 50.3 over e to the 0.2 h plus h. Based on this model, find the volume of the tank, indicate units of measure. Alright, so one thing to note when you're dealing with the AP exam is that this has to do with new functions, is that within a problem, an entirely new function that has nothing to do with the original function can be introduced. So it's as though you're dealing with a brand new problem. Okay, so that's basically the case here. This function f of h has nothing to do with the table. The only thing that we're going to be extracting from the table are our limits of integration. Alright, so we're still looking for volume, so let's go ahead and write down what the formula is here. So the formula for computing volume is the integral from a to b of the cross-sectional area, right? So in this case, the cross-sectional area is f of h. So it's going to be times of f of h dh. Okay, so that's the area. So you can write that, or integral from a to b of a of h dh, as we did in the first part. Alright, so we're just going to apply this function, this formula, to this function right here. So we're going to have we already know what f of h is, so the volume v is simply the integral, limits from 0 to 10. You extract that from the table of 50.3 over e to the 0.2h plus h. And then we are integrating with respect to h dh. Alright, so should I store this function in my calculator or not? Well, let me look at part D. Part D, using the model from part C. So we're going to be using the model multiple times, so it might be nice for me to store it. So let me show you how to store a function in the calculator so that you don't keep entering it over and over again. Okay, so we're storing 50.3 divided by, we have multiple terms in the denominator, so we're going to be using a parenthesis to group them together. So e to the 0.2h plus h. So that's the function. Let me just enter it to check error message. Okay, so I have a grouping error here. Let me fix that. The power needs to be separated, so close that, enter. Syntax. Okay, so let's take this parenthesis out of there. Bam. Okay, so I just enter the function into the calculator first before I store it. So the benefit of doing that is to make sure that what you're storing is precise. Now it's converting e to an approximation, so you can easily fix that by changing your approximation to, instead of automatic, I can make it exact. Okay, so enter. So what I just did is I pressed the mode button, and then I went to the second page, and then when you scroll down you have exact / approximation. You can make it exact, you can make it automatic, or you can make it approximation. So I chose exact because I want to make it look exact. Okay, so we have it right there. E 50.3, I would convert it into something else. Anyway, what I'm going to do now is I'm going to store this function into f of h. Okay, so store it as alpha f of h. Enter. Alright, so there you have it. So just take a look at what you stored. Focus on the left side because sometimes the calculator rewrites whatever you entered into a format that it likes. So this left side matches perfectly with what I have here, 50.3 over e to the 0.2h plus h. Okay, so we have it done. Now just to check to make sure that it did exactly what I wanted to do, I can just call back the function. So you call back the function f of h, bam. Okay, so f of h is stored. Now what we're going to do is compute the integral. So we're going to calculate the integral of this function. We're integrating with respect to h, so make sure that your variables agree with your function. And then we're going from 0 all the way to 10. Okay? Alright, so we don't want the exact answer, we want the approximate answer for this. So we're going to press pound enter to give me an approximate answer. Pound enter, and then it's calculating. There you go. The final answer is 101.325. So the volume here is 101.325. Now, do you notice what was indicated of us? We were asked to indicate the units of measure. So we already know what this is, right? We talked about feet squared times feet. So the unit for volume, you already know what that is feet cubed. So that's the volume of the solid where you have this as your horizontal cross section. Alright, let's take a look at the last part. It says water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at the rate of 0.26 foot per minute. Using the model from part C, find the rate at which the volume of water is changing with respect to time when the height of the water is 5 feet. indicate units of measure. Okay, so something to keep in mind, just a little tip, and this has to do with related rates. Now, how do you know that a problem is a related rates problem? Well, that's what this tip is for. If parts of a formula are changing with respect to time, think related rates. Okay? That's what related rates mean. Think related rates. The formulas are related with one another because of the formula. The parts of the formula are related by the formula, and we're looking at rates because we're changing each one of them with respect to time. So if you look at this right here, we have the height. The height is increasing at a certain rate, so h is changing with respect to time. And then it says the volume is changing with respect. It says find the rate at which the volume is doing what? Changing. So we're looking at the height changing and the volume changing. So we're looking at the parts of the volume formula changing with respect to time. So that automatically tells us that we are dealing with a related rates type scenario. Okay? Alright, so when you want to deal with related rates problem, first of all, you want to find the formula that relates to different measures that are changing. Okay, so what we need here, since we have height, and what else do we have? Volume. We need a formula that relates height and volume. But we have to use the model from part C. Check this out. We already have it down here. There you go. Bam. This is what we're looking at right here. This is the formula that relates the height, f of h dh, and the volume, v. So that's what we're going to be using. Okay, so let's first of all write down the formula that relates to different components. So v is equal to the integral from 0 to h of f of h dh. So for related rates, you write down the formula first, and then you differentiate with respect to time. We're going to be differentiating an integral here, so we are going to make use of the second fundamental theorem of calculus. Okay, so anytime you're differentiating an integral where at least one of the limits is a function, you are going to be using the second fundamental theorem of calculus. Okay, so notice that we're differentiating with respect to x and the function is x. So what you do is you basically plug in the function, the upper limit, into the function, and you multiply by the derivative of that function. In this case, we're differentiating with respect to x. So the answer will be f of x times dx. Dx is just 1. Okay? So times x prime, which is just 1. But in this problem, something unique is happening. I'll go over it right now. Check this out. So we're going to apply this formula here. We're going to differentiate this entire formula, both sides, with respect to time. So we're looking at the rate of change of the volume, ddt of v, equals ddt, the derivative with respect to time of the right side of the expression, this integral right here, derivative with respect to time of the integral from 0 to h of f of h dh. Okay, so notice the difference. In this one, we're differentiating with respect to x, and the upper limit is a function of x, f of x. So you do not have disagreement here, but here we're differentiating with respect to t, and this is h. So there is disagreement, so we have to differentiate implicitly, basically, and we're going to be adding the derivative of this function with respect to time as a component when we're differentiating the upper limit. Okay, so if you differentiate v to the first power using a power rule, it's just going to be 1 times, there's disagreement here, so it's 1 times dv dt. Okay, and then on the right side we'll apply FTC2. What you do here is you plug in the upper limit. So you have f of h, and you multiply by the derivative of h with respect to time. So the derivative of h, you can write that is not h prime. Okay, this is going to be h dot. So if you differentiate h, the derivative of h is just 1, but since there's disagreement, you have to add on dh dt. Okay, so this is a little tricky part of this problem. So we have the related rates equation, dv dt equals f of h dh dt. Now that we've differentiated the formula, let's now convert this into a simple algebra problem. We do that by writing down what you know and what you need, plug them in, and solve for what you need. Okay, so dv dt, the change in volume with respect to time. It says find the rate at which the volume is changing with respect to time. What does that tell us? dv dt is an unknown. We don't know what that is. Okay, what else? We're told that what else are we told? The height is increasing. It says when the height is 5 feet. Oh, there goes another piece of information. H is 5. When the height, at the instant that the height is 5 feet, the height is increasing at the rate of 0.26 foot per minute. So height changing, dh dt, that's what it means. The instantaneous rate of change of the height is 0.26. Okay? All right. So we are good to go. So this problem now becomes dv dt, which is what we're looking for. dv dt is going to be f of 5 times the derivative of h with respect to time, 0.26. Okay? Alright, another way to look at this dv dt calculation that we're doing is this is the same thing as v prime of evaluated at 5. That's basically what it is. Okay? Alright, so let's plug that into our calculators. We already have f of h stored in there, so all we're just going to do is type in the command f, the function evaluated at 5, okay, multiplied by what? 0.26. Well, that's the exact answer. Let's make it an estimate. 1.69442. So dv dt when h is 5, so dv dt is going to be 1.694, what was it? Let's call it back, 69442. Okay, your answer has to be accurate to 3 decimal places, but I like to encourage students to go to at least 4, so you have a margin of error there. Okay, now are we done with this problem? The answer is no. You are asked to specify the units of measure. Okay, so what are the units of measure here? So we talked about this earlier. Remember, we stated that when you're looking for the units, a lot of times the formula can help you determine exactly what you're looking for. Okay, so what are we looking for in this problem? This problem we found dv dt. So does this tell us the unit? Absolutely. This v is volume. What's the unit for volume? Feet cube, or you can say cubic feet, right? Time, what's the unit? The t is a time unit. What's the unit for time? You gotta be careful. You gotta go to the problem and look at what it says. So it says per what? Minute. Bam. That's the unit for time. So the time unit here is in minutes. So guess what? dv dt is feet cubed per minute. So The answer to this problem is 1.69442 feet cube per minute. Or you can say 1.69442 cubic feet per minute. Okay, cubic feet per minute. And that's that. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about this presentation, just post it in the comment section below, and we'll be glad to support you. Don't forget to subscribe to our channel for updates to the remainder of this FRQ review series or other math resources to help you. More clips can be found on mathgotserved.com, including great prep resources to aid you in passing the AP Calculus exam. Thanks again for watching, and have a wonderful day. Goodbye.